Hi Edgar. So here are a couple of examples that I'll work through and I hope they help. So if you've got a improper or indefinite integral, there will be a problem with a value that you would substitute into the integral. And often that happens when you substitute in 0 into rational functions. And that's what's happening with question A. So if I try and work through this integral, if I just do a quick sketch of the graph, we'll have a problem, because if I want to substitute 0 in, 1 over x squared is actually undefined for that. So if we have any integral that includes 0 or crosses over 0, so maybe if I wanted to find this integral, then I'm going to have a problem, because part of the range of values that I'm substituting in is undefined. It doesn't mean that you can't always find a value for it. And as you do more work in year 13, you'll see that for some integrals you can actually get a solution. But for this one, we're going to see that you don't get a finite answer, okay, which is fine. It's just, you've just got to demonstrate that you know how to work with these problems. So what I'm going to say is that, yes, I do have a problem with 0, so I'm going to avoid it. It's basically what we do in maths. So this integral would be the same as if I take the limit when n tends to 0 from n to 1. And that basically means that I can go and do this integration, because I'm basically going to analyse what happens when n gets closer and closer to 0, and then I'm going to analyse it, and I'm going to make a conclusion as to whether I can actually get a finite value for this integral, or if it's indefinite, or I just can't find a solution to it. It's very similar to your differentiation by first principles. You do loads of like algebra working, and then you analyse what happens when that small value of h tends to 0. Okay? So that's the trick. That's what we want to do, and it will be the same trick when I do this one. I'm going to write infinity. I'm going to write n instead of infinity, and then I'm going to analyse what happens to n when I tend to infinity after doing the integration. So let's go through and do the integration. So it's not the most challenging. So we get minus 1 over x, and I'm going to evaluate that between 1 and n. And that means that's equal to the limit when n tends to 0. When I substitute 1 in, I get negative 1, which already is a bit odd, because all of the values here on my graph have to be positive, so that's already a bit weird. And then when I substitute, I'm then going to minus 1 over n. Okay, and getting to that point, we're doing quite well, but it's this line of working that's going to get you the full marks. So we're then going to say when n tends to 0, 1 over n tends to infinity. Yeah, so when you divide by a smaller and smaller thing, you get a larger and larger value, and that's what's happening here. So therefore, the integral between 0 and 1 is indefinite. Okay, it's an infinite value, and that kind of makes sense really, because if it's not bounded, if it doesn't touch this axis, I'm always going to get some more area. Okay, so let's go and do the other one. So this one I'm going to go the limit, as n tends to infinity. Oh, sorry, I've missed the actual first bit, haven't I? So this is part B, and we were going to go from 1 to infinity. There we go. And this time we had a problem with infinity. Because obviously if you don't know where the boundary is, where you're cutting off your area, then we've got a bit of a problem. So go 1, infinity. Okay, and I'm going to do the same thing. We're going to change that infinity, and I'm going to make it n. I'm going to do this, it's going to be the same integral, but a different limit that we're applying afterwards. Right, you can tell I haven't been at school. Handwriting's rubbish at the moment. There we go. Over x, and I'm going from n1, and that's the same as when I'm going to apply this limit. Still get my -1 that we had, but it's all silly. We get -1 over n, and then minus 1 when I put the lower limit in. Now, interestingly, this analysis step does give us a value, which is quite surprising. So when n tends to infinity, when we divide by a bigger and bigger and bigger thing, that means that this tends to 0. So therefore, it means that this expression that we've got is actually going to be 0 plus 1, so that integral is going to be equal to 1. Okay, which is a bit more surprising, but often from my experience, and not to give the game away of some of the work you'll do in year 13, when you apply that infinity to a rational function, so 1 over something, you're more likely to get a conclusion or a definite value because of this. Because it's going to tend to 0, and that means that that term disappears. When you apply 0 to a rational function, you're going to get infinity. So you're less likely to get a solution. Okay, it's not a hard and fast rule, but often that's the case. Okay, and yeah, there's lots of analysis work that you would do in a maths degree at university that would help you understand why that is, but it's well beyond the scope of the course. You just need to be able to, the A level, they want you to be able to work with this limit notation in a really similar way that you did with differentiation by first principles. And it is these lines of working that are the things that are really important to get the marks. So you're actually showing that you know why you've used that limit. Okay? I hope that's helpful. And yeah, it's not a huge part of the single course, but yeah, if you know how to apply that limit and analyse your answer, that's what we want. Okay. Yeah, take care. Bye.